Let's look at electron configurations for ions. So when you get an anion, it's negative because it gained electrons, so then you're going to add electrons to the electron configuration. Cations form when an atom loses electrons, so you take the electron configuration for the atom and you remove some electrons. So when you remove electrons for the main group elements, they remove in the reverse order of filling. So for aluminum is a main group element. Here's its electron configuration. So when we make the anion, we know from its position it's going to form a +3 ion. We're going to remove the 3p electron and then the 2 3s electrons. We're going to start at the end and go backwards. And so here we have the aluminum 3+ ion, and this is its orbital diagram. Okay, so main group elements are nice and predictable. For the transition elements, the transition metals, we're not going to necessarily go with reverse order of filling. We're going to remove the valence electrons first and then reverse order of filling. So looking at iron, here's iron's electron configuration. These are the valence electrons right here. We're looking for the largest, oops, I want to cross them off. We're looking for the largest number here. We've got 1, 2, 3, 4, and 3. 4. These are the valence electrons. So we're going to lose the valence electrons first. So take those off. This is iron 2+. So we just removed the valence electrons. Iron also forms a 3+ ion, right? So if you're going to lose one more electron, then you're going to take it off of the last one that filled. So 3d5. So this is the electron configuration for iron 3. Argon, this one's empty because those were the valence electrons. They got taken off first. And then we've got 3d5. You can see why that might be a good ion because you got half fill, right? It's nice. Any questions? So for for transition metals, you remove the valence electrons first. For main group, you just go reverse order of filling. Magnetic properties. Some metals are attracted to magnets and some are not, right? You ever tried to stick a magnet on something that's aluminum? It won't stick. But it'll stick to iron. They're both metals. What's up with that? Has to do with unpaired electrons. So we say that an atom or an ion is paramagnetic if it has some unpaired electrons, at least one. Paramagnetic things will be attracted to a magnetic field. It's because of that unpaired electron. The spin of that electron not being paired up with another one of the opposite spin creates a magnetic field. Diamagnetic atoms, or ions, all of the electrons are paired up, and so it's either not attracted at all or actually slightly repelled by a magnetic field. So one of the issues here is, how do you remember which is which, right? Para and di, those don't really say much, do they? Para makes me think of pair, P-A-I-R, right? Pair, that's not right. Di means two. So diamagnetic, all of the electrons go 2 by 2. They're all paired up. Paramagnetic's the other one, unpaired electrons. So di means 2, even though this sounds like pair, it's not spelled that way, it doesn't mean that, okay? Write the electron configuration and orbital diagram for each ion, predict whether each will be paramagnetic or diamagnetic. To do this, you have to look, unless you really have a great understanding of what's going on here, you really need to look at the orbital diagrams to see if you've got paired or unpaired. Okay, so cobalt 2+. So cobalt is in the fourth period, so we've got argon, and then what comes after argon? 4s2, right? And 3d, how many? 7? Yeah, 3d7. That's the element. So that's where you start. We want cobalt 2+. That means we have to remove 2 electrons. Cobalt is a transition element. We're going to remove the valence electrons first. So that's those 2. So the electron configuration is AR 3D7. You could put 4s0. That's sort of a style issue. Okay, let's draw the orbital diagram. So this is 4s and this is 3d. So according to this, where are the electrons? They're in the 3D, and there's 7 of them. 1, 2, 3, 4, 5, 6, 7. It's like putting little soldiers to bed or something. Are there unpaired electrons? Yes. Diamagnetic 2 by 2. Is this diamagnetic? No, it's paramagnetic. So cobalt 2+ is paramagnetic. Like so many things that we're talking about, unless you use these terms all the time, and I don't even use them all the time, I just use them when I teach this chapter, right? You can't just expect to remember which is which. If you've got some sort of a picture or a little trick, like dia means 2, they go 2 by 2, they're all paired up. You can think through that in like 5 seconds. Yeah. Yes. In order for it to be diamagnetic, these would all have to be paired up. Yep. So let's look at N3-. So nitrogen, well, there's helium. That doesn't help much, but we'll take it. Helium, and then 2s2, 2p, how many? 3. So that's nitrogen, the atom. This is N3-. We need to add 3 more electrons. So this 3 becomes a 6. And that's why nitrogen forms a 3- ion, because it gets that valence shell full. Now it has the same number of electrons as neon. So let's draw this. So here's 2s and 2p. And the s has 2 electrons, and the p has 6. 1, 2, 3, 4, 5, 6. Diamagnetic or paramagnetic? Diamagnetic. Di means 2. All these electrons 2 by 2, like Noah's Ark. All paired up. Diamagnetic. N3-, not attracted to a magnetic field. Cobalt 2+ is attracted to a magnetic field. Not because of its charge, that's electrical, but because it has 3 electrons with spin that's not paired up, and so it will be attracted to a magnetic field. Yeah? Pardon me? That is an excellent point. that aluminum should have one unpaired electron, and yet magnets do not stick to aluminum. You got me. I can't explain that one. I'm sure there's an explanation, but I don't know what it is right now. Okay, so what happens when we have ions? Let's make sure I didn't skip anything. There we go. What happens when we have ions? Well, a cation, you've removed electrons, and oftentimes you've removed all the valence electrons. Is that going to make the atom bigger or smaller? It should make it smaller, right? It does. Cations are much smaller than the neutral atom. There's lithium plus 1. Not only have we've removed basically the valence shell. So the cations are much smaller than the neutral atoms. There's a higher effective nuclear charge, because now what were core electrons become the outer electrons, and so the number of core electrons goes way down. Effective nuclear charge is greater, everything gets pulled in tight. Anions, this one makes sense also, we're adding electrons that should make it bigger, right? You've added one or more electrons, and you have not changed the nucleus at all. And so the anions are actually much bigger than the neutral atoms, bigger than we would expect, but it's okay. It's the lower effective nuclear charge. So anions are much bigger than neutral atoms, cations are much smaller. Iso is a prefix that means the same. So isoelectronic ions are ions that have the same electrons, the same number of electrons. So we can look at this series of ions, sulfide, chloride, potassium, and calcium. Right? They all have 18 electrons, the same electron configuration as argon. What's different is the number of protons in the nucleus. 16 protons, 17, 19, and 20. So 20 protons is going to have a stronger pull on the electrons, and so this is going to be smaller than the others. 16 protons, much less pull. This one's larger. It's actually twice as big, but we just need to know the trend. So ion size. Choose the larger atom or ion from each pair. Well, potassium or potassium ion. So think, well, what makes that an ion? Did it gain an electron or lose an electron? It lost an electron. We pulled something off. It makes sense that that one's smaller, right? So the atom must be larger. We're looking for the larger one. Fluorine or fluoride. Fluoride, because fluoride has an extra electron. You stick something on the outside, it makes sense that it gets bigger. These two pieces of chalk, I keep seeing them out of the corner of my eye, and they look like two little goldfish crackers. It's making me crazy. No, random distractions. Where's the squirrel? Okay, so now these two, this is a little trickier. We've got a cation and an anion, so we might just think, well, let's just pick the anion because that one must be bigger, but we need to be a little bit careful. So calcium and chlorine, turns out, are isoelectronic with argon. Okay, so then we can compare them. So which one's going to be bigger? The chloride. Chloride's going to be bigger. We've added electrons. The effective nuclear charge is smaller. Calcium has 20 protons. Chlorine has 17 protons. They've got the same number of electrons. This has a lower effective nuclear charge, that means the electrons are not held as tightly, and so they kind of roam a little further away, and that ion gets bigger.